Cloaking. It's one of the coolest technologies to come out of Star Trek, right alongside phasers and transporters. But is it science fiction or just plain science? Is it actually possible to make something look like it's disappeared? Dr. Andrea Alù of the University of Texas at Austin thinks so. With funding from the National Science Foundation and the Department of Defense, he and his research group are working on new ways of cloaking objects in their lab, and have had some impressive results.
Cloaking is an attempt to reduce the visibility of an object. So if we were trying to reduce the visibility to humans, then what we would try to do is to suppress all the light waves that get scattered or get bounced off the surface of an object in all directions and for all observers.
There's a lot of people worldwide that are working on cloaking right now. It's very hot topics, very exciting right now, and they all have different approaches. But this one's very unique.
We see things in the visible spectrum, a very narrow portion of the electromagnetic spectrum composed of the different wavelengths that constitute color. Light waves bounce or scatter off of an object and return to our eyes, which are effectively sensors that detect color, shape, and other features based on what scatters back to them.
When something scatters, what we look for is how the field is perturbed around the object. So if nothing's there, we actually see kind of a plane wave going by in time. When you put the object there without a cloak, what ends up happening is it bends the wave around it a little bit, and it also scatters it in different places, so it'll create like shadows behind it and stuff.
Current stealth devices make an object less detectable by absorbing the incoming wave or by redirecting it away from the observer. If no scattered wave is picked up, the object cannot be detected. However, stealth may be tricked by moving the observer or by detecting the shadow of the object. Cloaking works by placing something around the object that cancels the wave for all observers, even on the shadow side.
A lot of people I've seen have related it to like a rock and water, and you can actually see the water bending around the object. But if you were to put a cloak around that rock, it would literally just go right through it. It's as if it wasn't even there.
Alù and his group have successfully done this, cloaking a cylinder to sensors that observe microwaves. They utilize the longer wavelength of the spectrum because it's easier to demonstrate proof of cloaking, and it's more cost-effective. If our eyes saw microwaves instead of visible light, this cylinder would be invisible. The cylinder is 18 centimeters long, a little under 2 wavelengths. To conduct the same experiment in the visible spectrum, the cylinder would have to be about 1 micrometer long, or 100,000 times smaller. For scientific purposes, utilizing the microwave spectrum is much more practical.
It started really as a theoretical type of work in which people were trying to show that by using some special materials around an object, it's possible to isolate that object completely from the background and avoid any type of bouncing of waves. So that would make not only the object less reflecting, but also completely transparent. So even if an observer is placed on the back of the obstacle, it would see the source of electromagnetic wave as if there was nothing in between. So it suppresses also the shadow of an object.
The special materials Alù refers to are known as metamaterials. Metamaterials are manufactured to meet exact specifications using nanoscale technology and can be made to exhibit exotic properties that don't occur naturally.
Since about 10 years, the field of nanotechnology has exploded, and there is a lot of interest in trying to manipulate the material properties by changing the fabrication of these materials at the nanoscale, at the atomic scale, or at the macroscopic scale in different ways. So in general, that's what we do in my group. We try to see how to apply these metamaterials or these artificial materials with exotic properties to a lot of different problems.
The concept is straightforward. A test cylinder made of homogeneous, non-conductive material is placed in a container made of metamaterial specifically designed to fit around it. This is placed in front of a horn that illuminates the unit with microwaves. A robotic arm measures the scattered waves and then compares it to measurements taken without the cloak. The metamaterial cloak is manufactured so that its scattering signature, the way it scatters waves, is the exact opposite of the cylinder inside.
The technique works using what we call a scattering cancellation phenomenon. So when the two are combined together, the visibility of the object is completely cancelled, is zero. It's kind of a compensation between what the object would do and what the metamaterial would do. When you combine the two, you cancel the scattering.
Though conceptually straightforward, planning for this experiment is anything but easy. The nature of the work demands a lot of computation, so Alù and his team have used the powerful resources at the Texas Advanced Computing Center to facilitate the design and execution of their experiments.
Before we can even attempt an experiment, it's always good to have a tool that can kind of back us up and can tell us what the challenges might be. So in this sense, having supercomputing resources within our campus is great.
With just a regular desktop or something, one could wait for a week or longer. So it helps us out a lot, actually.
The possibility of cloaking no longer seems to be science fiction. It's happening right now in a basement lab at the University of Texas at Austin. There are, of course, limitations. We're not cloaking starships at this point. But one day soon, perhaps we'll have the ability to cloak larger objects, or objects that aren't homogeneous. And there are practical applications right around the corner, like near-field microscopy.
Right now, the most practical way of seeing small details of an object is to go very close to this object, because in that way you don't need a lens. You just pick up the fields very, very close to the object, and then you can see whatever detail you like. The problem of doing that is that you have a lot of back reflection from the tip of your microscope. So in this sense, the cloak that we propose can be a great tool to, on one hand, allow you to go very close to the object to be sensed, but on the other hand, avoid any back reflection or any scattering that can affect the measurement itself.
There's a whole multitude of real practical applications for this. But then there's also the cool part where you could make things, stealthy.